For which assignment?
For assignment 6, I want to say the 2D, didn't have the entry for CCl4 gas, so I used Google term. The table value wasn't there.
Oh,
CCl4 gas.
so it's the entropy.
The entropy of the carbon tetrafluoride gas.
CL4. Okay, so according to this here, the value is 309.7.
I use 365 in Google.
Okay.
Change or
no, that's fine. I'll accept that.
Okay.
Yeah. All right. So as I was saying, we were basically revisiting, because of course this is a topic you should have met in Chem 1, balancing equations. And I told you guys that you can at least try to balance redox equations in the assignment. Oh, by the way, I've made copies of this assignment, so let me give these to you now.
I had a question on safety while you're passing it out. If you're doing addition or subtraction, and like for the G, the free entropy, you got delta entropy minus delta T times delta S. So if delta S is say like 290.2, we divide by 1,000. It used to be 1 decimal place after the number, but it now becomes 4 decimal places divided by 1,000. So
right, so therefore you go based on that
initial one, right?
Okay.
So like here, I have a 284.4 joules. I converted it to kilojoules.
Okay.
And now when I add subtract, I have 2 decimal places here, and I.
Oh, but you have to do this first. You have to multiply this first. Okay. And then what we get from that now, when you add that, when you subtract this from this, you round off to the lowest sum of decimal places.
Oh, so then it would be the 2.
Right, exactly.
I see. Okay.
Okay, want to get a copy of the assignment, and you guys should have access to it because I published it yesterday. So, let me bring this up on the screen. All right, so, well, first, let me ask you this. Have you guys attempted any one of these or all of them? Yes, no, maybe so? All right, let me help you out with a couple of these. I'm going to leave the rest for you to do as far as balancing redox equations are concerned. Let me download this here. Okay, so for the first question, right, they gave you the unbalanced equation, and you're asked to balance it. So what would be the very first step in this process?
The oxygen.
Nope. First step? What would be the very first step? Oh, sorry. Somebody's saying that I neglected to share the screen.
Ensure that balance is not balanced.
Well, it's not balanced, for sure. Okay, so you guys out there in Zoom should be able to see my screen. Okay, so what's the first step in this process?
You can label which is getting oxidized, which is getting released.
We would do the oxidation, which is HCOOH to CO2, and then we would do the reduction, that's NO4 and N2 plus.
Exactly, you separate the equation into two half equations. So one half equation would be formic acid to form carbon dioxide, and the other half equation would be the permanganate ion to form the manganese 2 plus ion. All right. So that's the first step in this process. You separate the given unbalanced equation into two half equations. What's the next step?
Ensure the balance, right?
Move down to H2O.
Not yet. Before that.
Oh, the difference.
Nope. That's even further down. What's the next step?
Oxygens?
Nope,
You had water?
nope.
Which one's oxygen, which one's redox?
Well, I mean, well, this one would be the reduction half equation, and this would be oxidation. But the next step in balancing, please feel free to follow the notes that you wrote in class yesterday, because I went through the steps, all right, yesterday. So after separating the given equation into two half equations, what's the next step?
We would add the coefficients to the front to make sure the Mn would be balanced, and the Mn is balanced in CO2.
Well, I think the way I have it worded is that you balance all atoms excepting oxygen and hydrogen, right? You balance all atoms in the traditional way, you know, by putting coefficients. In this case, you don't need to do anything as far as that is concerned, because the manganese atoms are balanced and the carbons are balanced, all right? But in the future, that's what you have to keep in mind. The next step would be to balance all atoms excepting oxygen and hydrogen, right? So after doing that, which we don't need to do in this case, what would be the next step?
Balance the remaining ones?
Okay, so let's start off with balancing what first?
So the first you balance, you're saying the oxygen and the hydrogen.
Right, so you're going to balance oxygens first, right?
Okay.
How do we balance the oxygens?
For oxidation, we would add 2 hydrogen ions to.
Nope, we're balancing oxygens, not hydrogens.
But the oxygens are already balanced on oxygen.
Yes, so therefore, as far as that's concerned, you don't need to make any changes. But what about the second half equation?
Do we add hydroxide or water?
We add water to which side?
To the right side.
To the right side. And how many do we add to the right side?
2 water.
You sure about that? 4 water molecules, exactly. So that the oxygens are now balanced, all right? Then we balance the hydrogens by adding hydrogen ions, right? So what does that mean for the first half equation? We add 2 hydrogen ions to the right to balance the 2 hydrogens on the left, all right? What about the second half equations? To which side do we add hydrogen ions and how many? Exactly, 8 hydrogen ions. Okay, very good. The next step is?
You mentioned something yesterday about how you want the water to be on a specific side, right?
Right, basically you add the water to the side which is deficient of oxygens, because you're trying to balance oxygen. So if you have more oxygens on one side than the other.
No, I think you remember when they say, but I remember there's like water and there's hydroxide or something, and you add.
Oh, no, that's later on. That's later on. That's later on. That's when you're going from acidic environment to basic environment.
Oh,
right. Exactly, but that's later on. Okay, so we have balanced the carbons, we have balanced the manganese, we have balanced the oxygens, we have balanced the hydrogens. So what will be the next step in this process? Balance the charges. And let me warn you again, this is where students tend to screw up things, all right? So how do we balance the charges? You add electrons, right? So to which side would you add electrons? Let's deal with the first half equation here. Right, the side with the higher net charge. So for this first half equation, you have no charges here, right, on the left side. But here you have a total of +2. So to which side would you add the electrons, and how many would you add? 2 electrons to the right side, exactly. Okay, what about the second half equation? What's the total charge on the left side of this equation? +7. What's the total charge on the right side? +2, all right? So to which side would you add electrons and how many?
The left side, 5.
Exactly. All right? Okay, what's the next step?
And then you cancel out items.
Yeah, but before we do that,
You have to make it so the electrons are equal to each other.
exactly, we have to equalize the electrons. Because remember, for every redox reactions, the number of electrons lost and gained must be the same. as we have it right now, we have 2 electrons here for the oxidation being lost and 5 electrons being gained for the reduction. So how would we achieve the equalization of electrons? Exactly. So we multiply this one by 5 right throughout. So that becomes 5HCOOH to give 5 CO2 plus 10 hydrogen ions plus 10 electrons. And then for this one, we multiply right through by 2 to get 10 electrons plus 16 hydrogen ions plus 2 MnO4 minus to give 2 Mn2 plus 8 H2O. All right? Then we add, and as he suggested, in adding, you might have to cancel some stuff. So let's see, what will cancel out in this? Well, firstly, the electrons will have to totally cancel out, right? There should be no electrons left over, right? Is there anything else you can see canceling out in this at this stage? Right, so these 10 hydrogen ions would cancel out 10 of these, leaving behind 6. All right? So I don't think there's anything else to cancel out. So we have to write down what remains, which will be 5HCOOH plus 6H plus 2 MnO4 minus. And then on the right side, we have 5 CO2 plus 2 Mn2 plus 8 H2O. And that should be the final answer, right? But of course, I always tell my students, when you get to this stage, you check to make sure that everything balances, including the charges, right? So let's do that. Starting off with the hydrogens. Now, we have a total of 10 hydrogens here, plus 6, so that's 16 hydrogens, and that balances with the 16 hydrogens on the right, all right? And then for the oxygens, we have 10 oxygens plus 8, so that's 18 oxygens total on the left, and here we have 5 times 2, 10, plus 8, 18 oxygens, so the oxygens are balanced. And then the manganese, we have 2 manganese here, we have 2 manganese here, so that's balanced. And the charges. So the total charges on the left side will be plus 6 minus 2. So 6 minus 2, that's plus 4. And here we have 2 times plus 2 plus 4. So now we know that the equation is balanced because everything is balanced, including the charges. All right? Any questions about this one? Any questions?
In the beginning, when I said balance the equation, that wasn't right. So you're looking for balance by adding hydrogen, right?
Well, balance by doing, by going through the steps. You know, you have to go through all the steps. And as I said before, I think I said yesterday that in some cases of redox equations, you don't need to go through all this. You can balance it just in a traditional way. But for more complex one like this, if you were to try the traditional route, it will be, time consuming. So that's why this is a better way of going about balancing this type of equation. All right, any other questions? Oh, somebody says something in Zoom. Oh, okay. All right. No questions or no more questions? All right, so let me clear this here. And let's scroll down to the next one. Now, this one is a bit different because this one has only one reactant. So you might be wondering, how do you separate this into 2 half equations? And it's actually very simple. You just basically do this. HXeO4 minus to give XeO6, 4 minus, and HXeO4 minus to give Xe, right? So basically, you're starting with the same reactant for both half equations to give each product. There's a special name given to this type of redox reaction. It's called disproportionation, right? And basically what happens in these kinds of reactions is that some of the reactant molecules behave as the is undergoing oxidation, and some of the same reactant molecule will be undergoing reduction, all right? So that's basically what's being shown here. All right, so now that we have separated the equation into 2 half equations, what's the next step based on what we have done before?
balancing the oxygens.
No, well, we balance first,
Instead of the oxygens and hydrogen.
right, balance everything excepting oxygen and hydrogen, which would be xenon in this case, which are balanced here and balanced here, all right? So,
So you say accepting hydrogen.
right, so basically you look for all atoms excepting oxygen and hydrogen, and you balance those first.
How do you know if it accepts hydrogen?
No, not accept, except, in other words, all other atoms apart from oxygen and hydrogen. So like in this case, yeah, right, exactly. Yeah, no, my accent is different, so that's why you probably hear something different. But basically all other atoms from apart from oxygen and hydrogen. All right. So in this case, that would be xenon, right?
Yeah.
And as it is, xenon is already balanced. So we move on to the next step, which is to balance the
No, oxygen.
oxygens, right? So how would you balance the oxygens by?
Adding water.
Okay, so what does that mean for the first half equation?
You need to have water with the reactant side.
Okay, and how many would you add?
2.
2 water molecules. All right, very good. What about the second half equation?
We add 4 waters to the right side.
Exactly. All right, very good. What's the next step?
Now, ensuring the balance. So then adding hydrogen ions.
Mm-hmm. So you're adding hydrogen ions to balance the hydrogens. So what does that mean for the first half equation?
3 on the right side.
You sure about that?
4, 5 on the right side.
Exactly. 5 hydrogen ions on the right side. And what about the second half equation?
7 on the left side.
Exactly. 7 hydrogen ions on the left side. Okay, very good. What's the next step?
Charges.
Balance the charges. Okay. So what does that mean for okay, what does that mean for the first half equation?
2 electrons on the right side.
2? You sure about that? Let me see here. You have -1 here, total. And you have 5 minus 4, so that's +1. So, yeah, you're right. 2 electrons on the right side. Okay, what about the second half equation?
That's 6 electrons to the left side.
Exactly, 6 electrons to the left side to balance the charges. Okay, next step,
Multiply the top by 3.
multiply the top by 3. So you're gonna end up with 6 H2O plus 3 HXeO4 minus to give XeO6 4 negative plus 15 H plus 6 electrons, right? And the next step, of course, would be to add these two. So in adding these two, some things will cancel out. The electrons will totally cancel out, right?
That's nicely. You forgot to add the E in front of the X-gases.
I'm sorry?
The frame for.
Oh, right, thank you. Yeah, you're right. Thank you. Okay, so the electrons will cancel out totally. So what else would cancel out?
4 waters.
Okay, yep. These 4 water molecules will cancel out 4 of these, leaving behind 2. What else?
7.
These 7 hydrogen ions will cancel out 7 of these, leaving behind 8, right? And therefore, we write down what's left. 2 H2O plus, now, because these 2 are on the same side, we have to add them. So that will give you 4 HXeO4 minus. And then on the product side, you're going to have Xe plus 3 XeO6 4 minus plus 8 H plus, and that should be the balanced equation at this stage. But of course, again, we check to make sure that everything is balanced. So let's do that now. Starting with the hydrogens, we have 4 hydrogens here plus 4 here, so that's 8. That balances with the 8 on this side. We have 2 oxygens, 4 times 4 is 16 plus 2, that's 18 on the left side. And then on the right side, we have 3 times 6, that's 18. So the oxygens are balanced. And then we have 4 xenons here. We have 3 plus 1, 4 xenons. And then as far as the charges are concerned, we have a total of 4 negative charges on the left side. And on the right side, we have -12. -12 plus 8, that's -4. So therefore, the charges are balanced. But we're not finished yet because the question says we have to do the balancing of equations in a basic solution. This that we have here is in an acidic solution. So it goes to what you were asking earlier, right? Basically, to go from acidic to basic, what do? We look at the number of hydrogen ions present and we add an equal number of hydroxide ions. Okay, what's going on here? hydroxide ions to both sides. All right? Now remember, one H plus one OH minus will give one H2O, right? In this case here, we have 8H plus 8 OH minus, so that would give 8 H2O as a result. So when these two are added, you're going to get 8 water molecules. And then now we can cancel out two of these. These two will cancel out two of these, leaving behind 6. So your final answer is going to be 4HXeO4 minus plus 8 OH minus to give xenon plus xenon 3 xenon O.
On homeworks or on tests, do we have to put like the phases in, like solid, gas, aqueous?
Nah,
Okay.
not, yeah, I don't think that would be important when it comes to balancing redox equation.
What is it in general for like units, or like, you know, how you grade the time?
Oh, no. 6H2O. And this should be the final answer. If you do a quick check through, 4 plus 8, 12 hydrogen, 6 times 2, 12, 4, 4, 16, 16 and 8, that's what, 24. And then we have 3 times 16, 3 times 6, 18, plus 6, 24. As far as the oxygens are concerned, we have 16 oxygens plus 8 oxygens, so 16 and 8 is 24. 3 times 6, 18 plus 6, 24. And the charges, we have a total of 4 minus charges plus 8 minus charges, so that's 12, and then we have 3 times minus 4, 12. Okay, so this is the final answer right here. This is the final answer. And that's how you do that. All right? Any questions about this one? Any questions? Any questions? Okay, let's look at the next one. And I want you to tell me what to write down. So I want you to do this one without minimum, with as little help from yours truly as possible. So let me see here. Okay, so here's the next one.
MnO4 minus goes to Mn2 plus.
All right, hold on 1 minute. Let me get my pen together here. So you're saying MnO4 minus to
Mn2
Mn2 plus. Okay, and then
H2O2 to
H2O2 to O2. Okay, what's the next step?
top equation, add 4 waters.
Okay,
First you check the manganese.
okay, right.
So then you add 4 waters at the top, the bottom you add 2 hydrogen or 2 hydrogen ions
Okay, to the,
to the bottom, yeah.
well, you have to add water first. Oh, but you don't need to add water because,
You get the option.
okay, so basically 2 H pluses on the right. But what about balancing the hydrogens for the first one?
Then we gotta balance them, so we gotta add 8 to the left side.
8 hydrogen ions on the left side. Okay, what next?
Now the electrons of charge. So let's see, the top has 7 left, and the right has 2, so 5 electrons on the top side, the left side, top right.
What about the second half equation?
Bottom one is 2 on the right, 2 electrons to the right side.
Exactly. Okay, what next?
Multiply the top by 2, the bottom by 5.
Okay, so if you multiply this by 2, you're going to end up with 10 electrons plus 16 H pluses plus 2 MnO4 minus. And then on the right side, you're going to have 2 Mn2 plus 8 H2O. Okay, and then what about the second half equation?
5 H2O2 goes to 5 O2.
You multiply by 5, so 5 H2O2 to give 5 O2 plus 10 H plus 10 electrons. What next?
And you add 2 equations together,
Mm-hmm.
and you check to make sure balance, check the charges. And then to ensure that it's acidic, you ensure.
Wait, hold on. Let's add them together. So the 10 electrons here will cancel out here and here, right? What else will cancel out?
The hydrogen ions.
Right, so these 10 hydrogen ions will cancel out 10 of these, leaving behind 6. So you're going to end up with 5 H2O2 plus 6 H plus 2 MnO4 minus. And then on the right side, you're going to have 2 Mn2 plus 8 H2O plus 5 O2. And then we check to make sure that everything is balanced at this stage. Starting off with the hydrogens, we have 10 plus 6, 16. 8 times 2, 16, so that's balanced. in terms of the oxygens, we have 10, 5 times 2, 10, plus 2 times 4, 8. So that's 18 oxygens on the left side. On the right side, we have 8 plus 10, 18. So the oxygens are balanced. The manganese, we have 2 manganese here. We have 2 manganese here, so that's balanced. And then as far as the charges are concerned, we have 6 plus charges minus 2, so that's plus 4. And here we have 2 times plus 2 plus 4. So we now know that this equation is balanced. All right? Any questions about this one?
And then it's acidic solution, so we have.
Right, so you don't need to take that extra step for basic.
So if the acidic solution, it can also be fully, it doesn't have to be equilibrium, it can be fully dissociated, right? So this one.
Yeah, we're assuming in all these reactions, it's one direction.
Yeah.
All right? Okay, any other question? Any other questions about this? About this one?
That's the permanganate ion, right? Is it permanganate ion?
MnO4 minus.
Yeah, and that's fully soluble.
Yeah. In fact, for our purposes, we're going to assume, which is true in all these cases, that any ions present would be in an aqueous solution. Now, you may end up with, in some cases, you may end up with like a metal deposited or gas being used up, in which case, you'd use the appropriate symbols. But when it comes to balancing redox equations, we're not too concerned about the states. Whether or not it's a solid or liquid or gas.
Okay.
We're just focused on making sure that everything, is balanced. Okay, so you guys now should be able to do the rest of this, right? I'm going to leave those for you to do. So basically you have, if I remember correctly, up to and including H, I think it is. Yeah. Okay, so I'm going to leave those for you to do. Make sure you show all the work and all that good stuff. Now, let me get back to the PowerPoint. So now we're going to look at an example of an electrochemical reaction. And if you remember, I said that there are 2 types of electrochemical reactions. You have one type which basically uses a spontaneous reaction to produce electrical energy. And then the other type is where you use electrical energy to drive a non-spontaneous reaction. So the first type of reaction we're going to look at are the reactions that will occur in what we call galvanic cells. And this is an example of such a cell, right? So let me describe what's happening here. We have this setup here where in one beaker, we have a solution of zinc sulfate. In another beaker, we have a solution of copper 2 sulfate, right? And then we have 2 electrodes, 2 metals that are immersed in each solution. So in the zinc sulfate solution, we have the zinc metal here. We call this the zinc electrode. In this solution here, we're inserting the copper electrode, all right? And then you have this instrument here, which is called a voltmeter. A voltmeter is basically an instrument which measures what we call the potential between this arrangement and this arrangement here. And when we say potential, we're talking about the potential for an electric current to flow through the external circuit, which is right here, all right? So the greater the potential, the greater would be the amount of current that would flow through, right? So basically what will happen, you're going to observe that the voltmeter is going to read a certain potential difference between these 2 systems right here, okay? So when you set up everything, electrodes are dipped into the solutions respectively and all that, then a reaction is going to take place. In this electrode right here, what will happen is that the zinc metal will undergo oxidation according to this equation right here, right? The zinc will form zinc ions and 2 electrons, right? So the zinc ions will enter the solution and the electrons will enter the external circuit, right? And then what will happen in the case of the copper electrode is that copper ions from the copper 2 sulfate will gain electrons to form copper, right? So eventually what's going to happen is that the amount of zinc that was present before will be decreased because zinc will be reacting to form zinc ions. At the same time, the amount of copper that is formed here would increase. So if you weigh each of these metals before and then weigh it after, you're going to see that the mass of the zinc will be less and the mass of the copper will be greater than before, all right? So basically that's how the electric current is generated and flowed through the external circuit. The current arises from the fact that the zinc undergoes oxidation. In doing so, the electrons that are produced enters the external circuit and then will come into contact with the copper 2+ ions, which will reduce the copper 2+ to form copper. So you're going to have a deposit of copper on the copper electrode, all right? So basically you have two half equations, and we can write down the net equation by adding this equation to this equation, and you end up with this as your net equation, all right? So this is a reaction that will occur spontaneously without any external influences whatsoever. And this is basically, the principles behind this is basically also behind how cells work, you know, like in your car batteries or your watch batteries and so on. Basically, that's how they're basically operating based on the same principle here of a redox reaction taking place spontaneously, which produces an electric current, all right? Now, let me, some terms I need to define here. So this combination of the zinc dipped in the solution here, the zinc sulfate solution, we call that the anode, right? And the anode is where oxidation takes place. As we said before, the zinc undergoes oxidation to form the zinc 2+ and 2 electrons. Here, the cathode is where reduction takes place, right? As we said, the copper 2+ ions in the aqueous solution will undergo reduction by gaining 2 electrons to form copper solid, right? And this is true for all galvanic cells and actually true for all electrolytic cells as well. We're going to meet those later on. And you need to remember this. At the anode, oxidation takes place, and at the cathode, reduction takes place, all right? Okay, now...
What was the memory mnemonic? It was like anox and something else jumped them?
I'm not aware of any memory aid as far as that is concerned. I'm quite sure there is, I just don't know of any.
It's like red cat, anox, something like that. They had it in the book.
In the text?
Yeah.
Oh, really? Oh, okay. Well, whatever works, whatever helps you to remember. But I don't remember coming across any mnemonic that would help us to remember. I just remember oxidation, anode, reduction, cathode. That's what I do. Okay. Now, one thing I did not mention here is the role of the salt bridge, right? The role of the salt bridge is very important in terms of the whole setup, the cell setup, being able to continue to produce electrical energy for as long as you have ions present in the aqueous solution. So the next slide is basically going to explain the role of the salt bridge, and the role of the salt bridge is basically to maintain neutrality of each solution so that the electric current can be continued to be produced for as long as possible, right? So basically, if you're concentrating on what happens at the cathode, remember we said that the cathode, hold on, let me see something here. Okay, I think this is okay, I think this is an error right here because it says for the cathode, the oxidation. Yeah, this should be for the anode. For the anode, the oxidation of zinc leads up. Okay, yeah, this should be the anode. So please make a note of that. This should be the anode, right? Where oxidation would take place, that would lead to an increase in the zinc ions present, right? So basically, in order to maintain neutrality of that solution, the zinc ions will move into the salt bridge, and at the same time, the chloride ions will move into the solution, right? So as to make sure that the anode solution is neutral. And then now here, this should be the cathode. That's another error here. At the cathode, basically the reduction of copper 2+ at the cathode will result in a decrease in the concentration of copper 2+, right? And therefore you're going to have an excess of sulfate ions which are negatively charged. So what's going to happen in this case is that the sulfate ions will move into the salt bridge, and at the same time the potassium ions in the salt bridge will move into the solution in order to maintain neutrality. So that's the role of the salt bridge. If you did not have the salt bridge, then basically the flow of current will stop prematurely, right? You want it to continue for as long as possible, and therefore that's the reason why the salt bridge. And by the way, the makeup of the salt bridge is basically agar gel, which is soaked in potassium chloride, all right? That's the makeup of it. So that's the role of the salt bridge. Without the salt bridge, basically, the electric current will stop short prematurely.
It's related to like putting salt on ice in the northern states, right? When they drive on the icy road.
Well, that's different. That's actually a colligative property situation, because basically when you add salt to ice, you basically lower the melting point. So therefore it melts the ice, and therefore remove that kind of hazard when you're driving and so on. So that's kind of different from this right here. Okay, so that's the role of the salt bridge. All right, so let's see what next. So how do we measure the potential? We use an instrument known as a voltmeter, and that's what you're looking at here. And this picture is kind of dated because the voltmeters that are made now are much more sleek. But basically, you attach electrodes to the voltmeter and to the separate solutions, and basically you measure it, you get a digital readout of the voltage, right? And there are different terms that are used to measure or express the difference in potential. It can be called the cell voltage, the electromotive force, or the cell potential, right? The electromotive force, EMF, is a very old term because back in the day, it was thought that electrons are literally forced through the wires. But we now know that not to be true, but the term still remains in some textbooks and literature, right? There's a shorthand way of representing a cell using what is called a cell diagram. And basically, we use it based on the oxidation, or I should say the redox reaction that takes place. And this would be the reaction right here. So this is a cell diagram for the cell that we just showed you. So you start off with the anode, where oxidation takes place, right? Where you have the zinc solid, then you draw a line like this, and then you write down zinc 2+, and you include the concentration, and then you draw a double line like this. And then on the other side, where reduction takes place, you start off with the copper 2+, and its molarity, and then a line like this, and then the copper solid. So this is basically a shorthand way of describing what the makeup of the cell is. So this part represents 1/2 of the cell, so that's a half cell, and this represents the other half of the cell. And the way you write this down is that you start off with the anode on the left side and the cathode on the right side.
So the anode and the cathode, they put the substance into its ionization state, right? Is that what it's doing, or?
At the anode, oxidation takes place.
Yeah.
Now, you could have a situation like in this case, where you have something neutral undergoing oxidation to form an ion. But there are other instances where one ion forms another. So for example, you could have Cu2+ to form Cu3+.
Yeah.
Right? That would still be oxidation. All right. So you could start off with a neutral species, but you can also start off with an ion being oxidized to form another ion. Or you could have something like this, Mn2+ to form MnO4-. Again, these are both ions, but it's an oxidation half reaction.
How does it do it in there? So like it's like is it covered? Is it open? How does it?
Like this? Yeah, you can leave it open like you mean like you can have it like this. It's set up right here.
Yeah.
Where it now again, in this case here, we're dealing with, how should I put this? Substances that will not evaporate or they're not volatile. Now, if you're dealing with other substances, then you have to, create some other conditions to maintain. So for example, if a gas is produced or if something is volatile, then you'd have to make sure that everything is covered so that there's no escape of materials.
Yeah.
But in this case here, you have two aqueous solutions, which are very stable. They won't evaporate easily, so you can leave it open like that, and nothing untoward would happen.
They're providing electricity to that area. That's how it's.
Well, no, the electricity is created as a result of the spontaneous reaction. Exactly. So, like I said, in the case of like car batteries, for example, It's the same thing. You know, the setup, it's a bit more complicated, but the underlying principle is a redox reaction, which is spontaneous, which produces an electric current. You see what I'm saying?
Yeah, yeah.
So that's how these cells work. Okay, so, and that's basically what galvanic cells are. Galvanic cells are cells where you have a redox reaction taking place spontaneously, which produces electric current. All right? Okay, so let me clear this here.
Well, how do you go, just from like science perspective, like
Mhm.
zinc solid, how do you go to the zinc ion? Is it by like with water or?
No, the zinc solid is the electrode here. Like, let me go back to the diagram I showed you. The zinc solid is the metal that is dipped. Okay, let me see here. Dipped in the, here's a zinc metal here, which is dipped in the solution which contains the zinc ion. And this is the copper electrode, which is dipped into the solution with the copper 2+. So
the water just kind of.
right, the water basically is the medium for dissolving the ions that are present. So in the case of the zinc electrode, it's an anode because it undergoes oxidation. So this is the reaction right here. The zinc metal actually just dissolves to form zinc 2+ ions, right? Now there are some instances, and we're going to see actually immediately after the next slide, there are some instances where the metal electrode is inert. In other words, it does not react itself, not like zinc. Zinc is reacting in this case, right? But there are some instances where the electrode is inert. A good example of this would be carbon in the form of graphite, right? It only serves as a conduit between the external circuit and the solution in terms of electrons leaving and going, right? So there are some instances where a part of the electrode is an inert material that is dipped in a solution, right? But that is not the case of zinc. Another example of such an electrode would be platinum, which is the example we're going to see shortly.
The purpose of the salt bridge is so that ions can transfer back and forth.
Right, so the purpose of the salt bridge is to ensure that these solutions here are neutral, right? Because what's going to happen is that, okay, let's look at what happens here in the anode section. What's going to happen is that you're going to have zinc ions being produced. So that means that this becomes more and more positive, right? In order to maintain the neutrality of this, what will happen is that the excess zinc ions will move into the salt bridge and the chloride ion will replace it. And that maintains the neutrality so that the current can continue to flow, right? Now over here, copper 2+ is undergoing reduction to form copper, right? So basically, you're going to deplete the copper 2+ ions here. That will result in an excess of negative charge because now you have sulfate ions remaining, right? So you're going to have an excess of sulfate ions present in that solution. In order to neutralize that, some of the sulfate ions will go into the salt bridge and be replaced by the potassium ions, right? And therefore that maintains the neutrality, which allows the electric current to flow even longer, right? If you have a buildup of charge in any one of those, that would hinder the current flow in the external circuit.
And the copper 2+ was actually combined with the current copper to make more copper solid.
Yes. So, like I said, if you weigh the copper before and then weigh it after, there'll be an increase in the mass. Right, exactly.
If you leave it there for like a couple days, you can get like a ton of copper over time.
Well, I don't know about a couple of days. It depends. It depends on, well, one factor.
The reaction speed, right? How fast it's.
Right, and also how much ions you have present. Exactly. But yeah, if you leave it long enough, then eventually you're going to see, copper. Actually, this process here is used, well, actually it's reverse. It's kind of the same thing. I don't know if you're familiar with the term electroplating, right? So basically, if you want to produce a coat of a metal on a surface, I know that I don't know if they still do so today, but for cars, for example, when they have the frame of the cars, they dip it into a solution which contains a particular metal that you want to coat the frame with. And then you allow the electric current to pass through, and the reduction reaction, which plates out the metal, will just plate it onto the frame of the car. And I think they use that for electroplating like jewelry and other things too. I remember correctly.
Just to make it bigger, you're saying, just to make it.
Well, just to make sure you have an even coating of that metal on the surface of the frame, for example. Right, so, okay. So that's a galvanic cell. These are the different terms. That's a diagram. Okay, now here's the thing about measuring electrode potentials, right? It is in practice impossible to measure the electrode potential of one half cell, right? Because in order for you to measure the electrode potential of one half cell, you need it hooked up to another half cell, right? So there's no way of, measuring just the electrode potential of a particular half cell, absolutely, right? So what the powers that be decided to do was to choose a half cell which is considered to be the reference half cell, right? And we assign that half cell the value of 0 volts, right? And therefore, any other half cell that is hooked up to that half cell, whatever the potential that is measured, that is considered to be the potential of that half cell. So the powers that be decided that this will be the half cell which will serve as the reference, right? It's called the standard hydrogen electrode or sheet, right? And basically consists of an acidic solution right here, and you have a platinum electrode. Now, this electrode here is an inert electrode, all right? So it's not going to react. So let me just put inert here, all right? So it's not going to participate in any reaction. Basically, it allows electric currents to pass through, right? And a part of this standard hydrogen electrode is hydrogen gas at a pressure of 1 atmosphere being forced here, right? So basically, the reaction for this half cell is going to be this right here. This is the reduction reaction for this half cell. H plus from the acid solution, and you use hydrochloric acid, but you can also use hydrobromic, hydroiodic. I'm not so sure about sulfuric or nitric. But yeah, basically this is the reaction right here. And they have decided that the potential for this is defined as being 0 volts. And therefore, any other half cell hooked up to that is based on this being assigned the 0 volt value for its electrode potential. All right? So what we're going to look at next is what happens when we hook this up to a copper electrode and the, what's the other one that we use? Zinc electrode. All right? So which one is first? Okay, so this is a zinc electrode. All right? So basically, we have the zinc electrode here. Remember now, the zinc electrode is the zinc dipped in the solution containing 1 molar zinc sulfate. And then we have the standard hydrogen electrode, which is the combination of the acid solution, the platinum electrode, and hydrogen gas being forced here at 1 atmosphere, right? So we connect these two electrodes. Of course, we have to include the salt bridge, and we measure the voltage. And when this was done, the voltage was measured at, hold on, let me see if I can quickly get to that here. Oh, okay. Before I get to the voltage. So this is the cell diagram, right, representing this setup right here. And in this case, it was discovered that the zinc electrode will undergo oxidation. So this is the oxidation reaction right here. And the hydrogen electrode, which is where reduction will take place, where the H plus will react with the electrons coming from the external circuit to form hydrogen gas. So this would be the half equation for the anode, this would be the half equation for the cathode, and then you add these two together and you get your net equation, all right? So in terms of the actual measurement, if you look at the voltmeter reading, you're going to see that the total EMF of the cell is 0.76 volts. So what that means is that the difference in potential between the two half cells is 0.76 volts, right? Now, the standard EMF of the cell that we're trying to figure out, which is the zinc sulfate, because this is set as 0, right? There's an equation we can use to calculate the standard EMF of the cell, right? And that is simply the standard EMF reduction of the cathode minus the standard EMF reduction of the anode, all right? So basically, we know that the EMF of the cell is 0.76, and we know that this zinc electrode here is the anode, right? So therefore, all we have to do is put 0.76 where we have this here, and the cathode, which would be the hydrogen electrode, would be 0, right? And when we do that, whoops, right? This is what we get, right? 0.76, which is the difference, is equal to the EMF of the cathode, which is the hydrogen electrode, minus the EMF of the anode. And then we solve for the EMF of the anode, which is what we want, which is a zinc electrode, and that turns out to be equal to minus 0.76 volts. So basically what this is saying is that the potential of the zinc electrode is minus 0.76 relative to the hydrogen electrode, all right? So that's how we get the standard EMF value, or I should use the actual term. Standard reduction potential is, for the zinc electrode, is minus 0.76 volts, all right? Okay, any questions about this? Any questions? Any questions? Now, excuse me, what we're gonna look at next is when you do the same thing for the copper electrode. Excuse me. Oh, by the way, so basically this value here is for this reduction reaction, right? The standard reduction potential for the zinc electrode is for this reduction reaction, all right? Or reduction half reaction. Excuse me. So for the situation with the copper electrode, again, we hook up the standard hydrogen electrode to the copper electrode. So that's the setup right here. And what we'll notice is that the electrons will be flowing from the hydrogen electrode to the copper electrode, all right? So when the cell EMF is measured, it was measured to be 0.34 volts, all right? So using the same idea, oh, by the way, this is the cell diagram, and they're showing you here the oxidation. Now, the oxidation reaction would be the reaction taking place here, which is the hydrogen forming H plus and 2 electrons. The reduction reaction is a reaction taking place in this half cell where you have the copper 2 plus reacting with the electrons to form the copper. So when you add these two together, this is what you're going to get. H2 plus Cu2 plus to give Cu plus 2H plus, all right? So that's a reaction that will spontaneously take place. Now, in terms of the EMF of the cell itself, that is equal to 0.34 volts, right? The EMF of the cathode is for this right here. This is the cathode because this is where reduction takes place. And the EMF standard for the anode is the HCl, right? Electrode, or the hydrogen electrode, which will be 0, right? So when we put the numbers in, you're going to put 0.34 volts here, you're going to put 0 right here, and you're going to solve for the EMF of the copper half cell, and that is equal to 0.34 volts, all right? So what that is telling you is that the EMF potential of the copper electrode is 0.34 volts higher than that of the hydrogen electrode. And as a result, the electron will be flowing from the hydrogen electrode to the copper 2 plus copper electrode, all right? So that's how you get the standard EMF reduction potential for the copper 2 plus in this case. So in both cases, in the case of the copper 2 plus electrode and the zinc electrode, you basically hook them up to the standard hydrogen electrode, do your measurements, and therefore determine the standard reduction potential of your copper or zinc relative to the hydrogen electrodes. So, oh, I'm sorry, yes, sir.
So going here, determining which one's anode and cathode, how do you determine the reactance of each one? So like on the left one, you have H2, as we're talking, could it have ever been like 2H plus 2E minus goes to H2?
You have to look at how the electrons flow.
Okay,
So
it shows you electrons are going from the hydrogen.
Exactly. So the electrons are flowing from the hydrogen electrode to the copper electrode. Then that means that oxidation is taking place in the hydrogen electrode, which means that the hydrogen electrode is the anode.
Yeah.
And therefore the copper electrode will be the cathode because reduction is taking place there.
So it will always show us a diagram.
Right, exactly. It's all a matter of electron flow. Now, if you're not given the electron flow, but you know the potential of one and the other, then you can predict the electron flow, right? The one with the higher potential, right, will be the one that the electrons will flow to.
Yeah.
You see what I'm saying? So that's why in this case here, the copper 2 plus has a higher electrode potential compared to the hydrogen, which is 0. So therefore, the electrons will flow from the hydrogen to the copper. In the case of the previous one, let me go back to the previous one, where it's the other way around. Okay, in this case here, the zinc electrode we determined to be minus 0.76 volts. So that's negative, right? So that means electrons will be flowing from that to the hydrogen electrode, which has a higher potential. Exactly. So if you're not given the flow, you look at the relative potential of one electrode to the other, right? To predict the flow of electrons in the external circuit. Okay, so I was about to say that people have gone through the trouble of doing what we just described to get values for different electrode reduction potentials, right? And there's a table, a very small table, believe it or not, that is shown right here, right? And if you look at this carefully, basically you're going to see that these different reduction, these are all reduction half reactions, by the way. All of them are reduction half reactions where you have something reacting with electrons to produce whatever, right? And what they have done is that they have gone through and determined the electrode potential, just like how we described it, for each of these half cells, right? And what they have done is that they have arranged it in order of decreasing values. So the highest would be the fluorine reduction potential, which has a value of plus 2.87 in this list, and then they just continue listing the others in terms of their electrode potentials, right? Now, I've provided an even more comprehensive list in Canvas. Let me show you where that is. So let me go to Files. Okay, let me go here. Then let me go. Okay, where is it? Tables. And then, okay, so here where it says standard reduction potentials. So this is several pages long. 4 pages. All right, so this is what you're going to have access to, all right? So basically, again, they list the electrode potentials according to the reduction half reactions. So for example, here's the fluorine one that we saw before. Fluorine plus 2 electrons to give 2 fluoride ions, that's the electrode potential, all right? And if I remember correctly, this is arranged in order of the electrode potential value, but I think they also have another arrangement in terms of alphabetical order. Right, here, where it says standard reduction potential at 25 degrees Celsius in alphabetical order by redox couple, right? So in this case, for example, the first one in this list is silver 2 plus 2 electrons to form silver plus, and the value for that is 1.98, for example, right? So you're going to have access to this table in order to solve problems when it comes to calculating standard reduction potentials and so on. Okay, so let me go back to the PowerPoint and make some points here in regards to the reduction potentials and how we can use them. So the first thing I'm going to say here is that the standard reduction potential is for the reaction as written, right? So basically for, like, for example, the first one, the reduction potential, which is 2.87, that is for the reaction of fluorine plus 2 electrons to give 2 fluorides, right? So that's the first thing you need to be aware of. The second thing you need to be aware of is that the more positive the reduction potential, the greater the reduction reaction will take place, right? Or the greater the tendency of the reduction reaction to take place, right? So what that means is that if you were to compare, let's say, the first one with the second one, right? The first one is more likely to occur in the same system compared to the second one, all right? Because the first one has a value of 2.87, the second one has a value of 2.07, all right? The next thing I want to say is that half-cell reactions are reversible, right? So in other words, for this half-cell reaction, you can have the fluoride reacting to form fluorine and 2 electrons. So that begs the question, how does that change the reduction potential? And the answer is that the sign changes. So this is kind of similar to what you learned with respect to like delta H or delta G or entropy delta S, right? If you reverse the half reaction, then the sign changes, right? So for the first one, if you reverse the reaction where you start off with fluoride and end up with fluorine, then the value of that reduction potential will be minus 2.87, all right? The next thing I want to say here, and this is where there's a big difference between electrode potentials and the other thermodynamic quantities, and that is that changing the coefficients do not change the value of the reduction potential, right? So in other words, if I were to multiply each of these by 2, so that's 2, that's 4, and that's 4, right? The value of the EMF does not change, all right? So that's one important difference between the reduction potential and, other terms or other quantities like enthalpy, right? Because we all know enthalpy, you have to multiply by 2 if you double everything in the equation, right? But that is not true for electrode potentials, all right? Okay, so those are some things you have to remember when it comes to handling these numbers. Okay, so let's look at this example. This question is asking, what is the standard EMF of an electrochemical cell made up of a cadmium electrode in a 1.0 M cadmium nitrate solution and a chromium electrode in a 1.0 M chromium 3 nitrate solution? All right, so the first thing I would do is go to the table, just like the ones that I just showed you, right? And I would look up the, oh, you have a question?
Yeah, with the cathode anode, how would you reverse the electrons are flowing from one to the other? How do you just?
Okay, it depends on what they're hooked up to,
Okay.
right? So let's say you have an electrode which has a certain value here, and the EMF value of the other electrode is higher,
Yeah.
right? That means electrons will flow from this electrode to, right. Now let's say that instead of this one, you have one where its value will low. Then what's going to happen? The electron is going to flow from the lower one. Exactly. So it depends on the relative, what's the word I'm looking for? The relative sizes of the reduction potential that you're hooked up to, right? So you can have one half cell where the reaction is going in one direction depending on what it's hooked up to. But if it's hooked up to another one, it's going to reverse. Exactly. Okay, so as I was saying, what I would do first is go to the tables and look up the reduction potentials for these half cells. So in the case of the cadmium half cell, its reduction potential is minus 0.40 volts. In the case of the chromium half cell, its reduction potential is minus 0.740 volts, right? So to get the standard EMF, what I would do is look at these two values and decide on which one is of a higher value. And the one that is higher in value is the one that is more likely to occur as written, right? So the higher value one would be the minus 0.4 volts, right? So I would leave that alone. And what I would do is flip this one, right? So when I flip it, right, you're going to get this right here, chromium forming chromium 3 plus 3 electrons. And notice what happens to the sign. The sign changes from negative to positive because you flipped the equation, right? So basically, the two reactions that would take place would be this reaction here, which is as a result of flipping this, and this reaction here, which will remain the same because its EMF value is higher compared to that one. So that would be the reduction half reaction. And then you add these two together. Now remember, when you're adding these two, you have to multiply, you have to make sure that these electrons are equalized, right? Which means you have to multiply this equation here by 2 and this equation here by 3. Right? So you're going to multiply this by 2, multiply this by 3, right? However, remember what I said, that will not change these values, right? So even though you multiply this equation by 2 and multiply this equation by 3, these values will not change. So when you multiply this by 2, you're going to get 2 times this plus 3 times this, and you add them together, and this would be the net equation right here. And then to get the net EMF value, you simply add these two numbers together and you're going to get 0.34 volts, right? And that would be the answer. That would be the standard EMF of the cell created by these two half cells, right?
How do you know how to flip equation number 2?
Because equation number 2 has a lower EMF value.
So we have a standard EMF of a cell,
Mhm.
with two different, polyatomic ions, or two different compounds. Then we're gonna have to have two different reactions in the lower one, well, this one needs to be flipped.
Exactly, because the one that has a higher EMF value is the one that is more likely to remain or to occur as written,
I see.
right? So that means that the other one has to be flipped,
I see.
right? Because that is less likely to occur as written. It's more likely that one would occur in the reverse direction.
Essentially, the first one is stronger, so it's gonna take the electrons there and the other gonna.
Exactly.
Respond to that to the opposite. Okay.
And then you multiply by whatever and then add them together.
Yeah.
Now there's an easier way, even though I really don't prefer this way, even though it's easier to do this, to solve this problem, to get the same result. But I don't like it because it doesn't show step by step like what we did here. But let me just show you anyway. So another way of doing this problem is that we use this equation right here. The EMF of the cell will be equal to the standard EMF of the cathode minus the standard reduction potential of the anode. And then all you have to do is consult the table and look up these values, which will be these two values right here. But you have to first identify which is the cathode. The cathode is the one with the lower EMF value. All right? So actually, I'm sorry, the cathode is the one with the higher EMF value because that's where reduction takes place. So this minus 0.40 volts would go here, and this minus 0.74 volts would go here, right? So it's minus 0.40 minus 0.74, and that gives you the same answer, which would be 0.34 volts. So you can actually do the calculation that way. But personally speaking, I prefer this way because it shows you step by step how you arrive at your final answer. All right? Okay, any questions about this one? Any questions?
Well, if you can always identify the cathode, this way.
Exactly right. And the way to identify the cathode is basically the one with the higher. Exactly. The one with the higher standard reduction potential. Okay. Any other questions about this? Any other questions? Any other questions? All right, let me see. Okay, so let's go back to the assignment. So let's see what question. Okay, so, all right, so question number 2, it says, let me make this a bit smaller because, okay, so question number 2 says, create a functional galvanic cell given the following. On the left side of the cell, you have a 1.0 M aqueous solution of oxalic acid with an inert platinum electrode. On the other side, there's a solid iron electrode sitting in a solution of 1.00 M iron 3 nitrate. Right? Then it says finish drawing the cell and label the anode, the cathode electrodes, solutions, and all parts of the cell. Write and balance the half reaction and overall cell reaction. Calculate the EMF of the cell, delta G and K. Okay, we won't be able to do delta G and K quite yet, but let's focus on the other parts. Indicate where all the charged particles flow and their identity, and then it says write a shorthand notation for the cell, and you're going to use the data from the tables that I just showed you in order to complete this chart, right? So according to the information provided, the left side will contain a 1.0 M molar solution of oxalic acid. So the first thing I'm going to write down here is I'm trying to get everything fitted onto this. Okay. So the first thing I'm going to write down here is that over here, I'm going to have 1.00 M oxalic acid, H2C2O4. And then the other solution would be 1.00 M FeNO3. 3. All right? Okay. Now, okay, let me see what the question on the other side. Finish drawing the cell, label the anode, cathode electrodes, solutions and all parts of the cell.
And the
Okay.
table so the table, are we looking for a specific like H2CO?
Exactly, right. So, yeah, you're gonna look for the reaction that would involve the oxalic acid, which I did already. Because I didn't want to waste time searching. So basically, if you look up in the table, let me just put it right here. You're gonna see this. 2CO2 plus 2H plus 2 electrons.
Does the table have the whole reaction like?
Exactly, yeah. To give H2
C2.
C2O4, right? And when you look up the EMF value for that, that would be equal to minus 0.43 volts, right? And then if you look up for the Fe3 plus 3 electrons to give Fe, you're going to see that the EMF value for that is equal to minus 0.04 volts, right? Okay, so when we look at these two, just like we saw in the previous example, we have to ask ourselves, which one will serve as a cathode? And the one that will serve as a cathode is the one with the higher standard EMF value, which would be the
Iron.
exactly. So basically, the iron here would be the cathode, right? And the one with the oxalic acid would be the anode. All right? So what does that mean? That means that the oxidation half reaction would be the reverse of this right here, right? For the oxalic acid. So here we're going to put H2 C2O4 to form 2CO2 plus 2H plus 2 electrons, all right? And the EMF of that would be this, but the sign would change. So this would be plus 0.433 volts, 43 volts, all right? So that would be the oxidation half reaction, right? And then for the reduction half reaction, I have to scroll down. Okay, that's going to mess up things a bit. Let me clear this here. Okay, so I'm just going to rewrite what I just erased here. So this would be the oxidation half reaction to form 2CO2 plus 2H plus 2 electrons. And the EMF of that would be 0.43 volts. And then now for the reduction half reaction, that would be Fe3 plus 3 electrons to give Fe. And the EMF of that would still be minus 0.04 volts, right? So when you add these two together, right? Of course, you have to multiply this by 3 and multiply this by 2. You're going to get 3H2C2O4 plus 2 Fe3 plus to give 6 CO2 plus 6H plus 2 Fe, right? So that would be the net reaction, and the EMF of the cell would be this sum of these two, which would be 0.43 minus 0.04, and according to my calculation, that would be 0.39 volts. All right?
So we remove the nitrate or remove the nitrate because it's super soluble.
Well, the nitrate is just basically a spectator ion in this thing.
Yeah.
Right. So it's not involved in this reaction.
If our equation was like Fe3 plus NO3 minus to get Fe NO3.
Right, then in that case, you'd have Fe3 plus in one electrode, the nitrate in the other electrode, and then you do just like what we did here in terms of, the redox. But you'd have, in addition to that, you'd have to go to the table to look at the search for the half reactions involving those species.
You would find it because it's not.
Well, I'm quite sure there's equations in there for nitrate, for example. So it all depends. So basically, you have to use that table to look for half reactions where those species are involved. All right? Which is what we did here in this case. So did I complete the table?
We use, what are we going to use the iron piece of the nitrate? Nitrate is soluble, right? It's spectator ion.
Well, the nitrate is spectator ion, and let me see here. And also, if oxalic acid is the anode, if oxalic acid is the anode, which gives off electron, the electrons will move over to the cathode. You have to ask yourself which species is more likely to be reduced. And the answer would be the Fe3 plus, and you'd have to use the electrode potential values to predict that as well. Okay, so I think we have completed the table because basically, as I said before, this is 1 minute.
That's 0.39 volts, right?
Yes, sir. Okay, why is this thing not behaving itself? Oh, no. I didn't need to do that. So this would be 1.00 M oxalic acid. And this is 1.00 M iron 3 nitrate. And I think that's pretty much, oh, we need to show the electron flow, my bad. All right. Which means I need to scroll up. So basically, as I said before, the oxalic acid is the anode, right? Which means that the electron flow would be in this direction, right? Because this is the anode and this is the cathode. Okay, so
What are the electrodes? How do we show them?
yeah, that's a good question because as far as I'm concerned, the anode and cathodes are the electrodes.
Okay.
So yeah, I'll leave that alone.
But it's just labeled anode, cathode.
Right, that's-
Solutions and the electrodes.
Right.
Electrodes kind of, that shouldn't be there. That's.
Yeah, I don't think, yeah.
But it's for the vertical area, not the separate.
Oh, that's the saw bridge. Thank you. Yeah. Saw bridge. And I think that's it as far as labeling is concerned. I don't think there's anything else we need to.
Do we need to put like the ions in the solution or?
You mean in the saw bridge?
Yeah, that's sort of like in the.
They didn't require that, so
We don't need to put like the non-brigade in the.
yeah, because well, that is indicated where we said solutions. We indicated that, you know, one solution is 1 molar oxalic acid, the other solution is 1 molar iron 3 nitrate. So I don't think we need to put anything else. I think we have completed this table. I don't think there's anything else we need to add to this. Okay, we can't do delta G yet or K before we move on to other topics. So that means we have to go back to the PowerPoint. All right, let me clear this here and go to the PowerPoint. So, okay, so let's talk about the spontaneity of redox reactions. So remember in the previous chapter in thermodynamics, remember we defined spontaneity as basically for a process, basically meaning that the process will occur without any external forces or assistance, right? So we learned about delta G. Delta G is basically gives free energy, which is what we use to make predictions as to whether or not a reaction is spontaneous, right? So it turns out that there's a relationship between delta G and the EMF of the cell, and that's given by this equation right here. Delta G is equal to minus N times F times the EMF of the cell. Now, N represents the number of electrons that is transferred when the redox reaction takes place. And F is a constant known as the Faraday constant, right? And the value of the Faraday constant is 96,500 joules per volt per mole. Another way of expressing this combination of units is coulombs per mole. And coulombs basically is the metric unit of charge. So this combination of units right here is the same thing as coulombs per mole. And coulombs is spelled I think it's C-O-U-L-O-M-B.
Coulomb is like work electricity, right?
Coulomb is a measurement of charge, right, on the electron. And while I'm at it, I would say also that one electron has a charge of 1.6 times 10 to the minus 19 coulombs, if I remember correctly. Yeah, something like that. I could be wrong, but I think that's it. Okay, So that is Faraday's constant. Now, this here that I show you first represents the free energy relationship between free energy and the EMF of the cell. And if you're talking about standard conditions, then this is the equation that describes that. So the only difference between this and this is that this is for standard conditions. Remember, standard conditions would be temperature at 25 degrees, pressure of gases at 1 atmosphere, solutions molarity to be 1 molar, and all that good stuff. All right. So, oh, I added there. So let me just clear this. There was no need for me to write it up because it's there presented in the PowerPoint. Okay. Okay. Now we already know this equation right here. Delta G standard is equal to minus RT ln K. So therefore, these two expressions are equal to each other. So we can set them equal to each other like this. And then we can rearrange it to get this equation right here. The standard EMF of a cell is equal to RT over NF times ln K. All right. So this is the relationship between the EMF under standard conditions for a cell and the equilibrium constant, right? And you'll notice that there are several constants involved. There are two constants involved. One is R and one is F. R is the molar gas constant and F is a Faraday constant, right? And if the conditions are standard, that means that the temperature will be constant as well, 25 degrees Celsius, right? So basically we have three constants involved in this equation right here, right? So that is R, that's the temperature, and this is, of course, the Faraday constant. So basically, we can reduce this equation to this right here. So basically, when you work out all of this right here, you're going to end up with 0.0257 volts over N times ln K, and that will be equal to the standard EMF of the cell. All right? And there's yet another way of expressing this. If instead of using natural log, we use log to the base 10, then this equation becomes this equation. So you can use this equation here, or this equation here, or this equation here to solve for the standard EMF of a cell if you know what the equilibrium constant is. All right? Okay, what's next? Okay, so this is just basically a summary of the relationships between delta G, the EMF of the cell, and K, right? So basically, whichever equation you use is dependent on, the type of question you're given, right? So if you want to calculate, for example, the delta G for a cell, if you know the EMF, then this is the equation you use. If you want to find delta G based on the K value, then this is the equation you use. If you want to find E for the cell, depending on the K value, then this is the equation you use. So it all depends on, the question you're given. Okay, some other aspects of the relationship between delta G, K, and the EMF of the cell. Let's look at what happens if delta G is negative. So this is the equation right here. If delta G is negative, then what does that say about K? That means that K would be greater than 1, all right? And if K is greater than 1 and delta G is negative, that means that the EMF of the cell would be positive, right? Because of this negative sign right here. So if delta G is negative, that means that the EMF of the cell is positive. So what does that mean in terms of the spontaneity of the reaction? That means that the reaction would favor the formation of the products. Now, if delta G is equal to 0, that means that K is equal to 1, which means that the EMF of the cell under standard conditions would be 0. What that means basically is that the reactants and products would be equally favored in terms of which one will be formed, all right? And then now, in terms of delta G being positive, that means that K would be less than 1, which means that the EMF of the cell will be negative, which means that the reaction would favor the reactants, all right? Okay, so that's basically just a description of the relationship between delta G standard, the equilibrium constant, and the EMF standard, all right? Okay, so let's apply that to this example right here. What is the equilibrium constant for the following reaction? And it gives you the equation, right? So the first thing I would do is I would write down the equation for the EMF of the cell, because that will show you, well, if you get that, then this is the relationship that you're going to use to get the K value, all right? So we have to look at each reaction or each half reaction that's occurring, right? The oxidation half reaction is where the silver will form the silver ions, and the EMF of that, you'd have to look up that. In the case of the iron, the reduction will take place, which is this right here, right? So basically, when you add these two together, you're going to get your net equation. Now, 2 electrons are going to be lost here, 2 electrons are going to be gained here. So the N here is equal to 2, right? And then now you calculate the EMF. You can do it this way, where EMF would be equal to the EMF standard for the reduction half cell minus that for the cell where oxidation is taking place. So this is the cathode, this is the anode, right? So when you look up the values, this is what you get. For the cathode is minus 0.44, for the anode is minus 0.8. So you add those two together and you get the standard EMF value being equal to minus 1.24 volts, all right? So that would be the EMF for this reaction right here. So basically what you're going to do now is put this value where the standard EMF of the cell is, and then you solve for L and K, right? So K, when you rearrange it, will be equal to E to the N times E of the cell divided by 0.0257. So that's what you get here. And then you put the numbers in, and then you do your number crunching. And according to this, the answer should be 1.23 times 10 to the minus 42. And based on what I see here, let me see here. Let me see something here. I think there's something off with the sig figs.
How do you know that N is 2?
Because you have 2 electrons lost here,
So,
2 electrons gained there.
so N refers to the amount of electrons.
Right, the number of electrons lost and gained. Let me see something here. 1.24 times 2, that's 2.48 divided by 0.0257, 96.5. So this is okay. When I worked out this part here, I got minus 96.5. Now this is 1 decimal place. That means this should be 1 sig fig, right? So make a note of that. That should be 1 sig fig, all right? Okay, any questions about this one? Any questions? All right, let me clear this. In fact, let me do this here. Okay, let's look at the effect of concentration on the cell EMF, right? Now it turns out, and I think we made this before, delta G for reaction is equal to delta G standard plus RT, L, and K, right? Now, delta G is also equal to minus NFE, right? So if we replace delta G with minus NFE here, and delta G standard with minus NFE standard here, this is what you're going to end up with, right? And then if you divide right through by by minus NF, you're going to end up with this equation right here. And this equation is called the Nernst equation, right? And this equation shows you the relationship between the EMF of the cell and the concentrations of the cell, which would be a part of the reaction quotient Q here. Now, if the temperature is set at 219 Kelvin, that means that R will be constant, T will be constant, F will be a constant. So this simplifies to this right here. And if you're going to change from natural log to the base 10, you're going to end up with this equation right here. All right, so you can use this form of the equation or this form to solve, for this EMF if you know everything else. Okay, so here is an example of this, where the following reaction occurs spontaneously at 25 degrees, and it gives you the concentration of the different species involved. And it gives you also the equation, right? Okay, so first we have to identify what is being oxidized and what is being reduced. So in this case, it's the cadmium being oxidized and the iron 2+ being reduced, right? So these are the two half equations, all right? The next step would be to, of course, you have to make sure that you know what the number of electrons being lost and gained would be. So N is equal to 2 in this case. And then now the EMF of the cell, under standard conditions, you'd have to determine by looking up the values for iron and cadmium. So when you look them up in the tables, you see that for iron, it's minus 0.44 volts, And for cadmium, it's minus 0.40 volts. So you do the calculation here, and you will end up with minus 0.04 volts. So that will be the standard EMF. But the question is not asking for the standard EMF. It's asking, will the following reaction occur spontaneously under these conditions? So therefore, you need to find the EMF under those conditions, right? And that's where Nernst equation comes in. So this is the equation right here. So we have already calculated this right here, minus 0.04 volts. That would go here. Now the question is, what goes here? What is a Q? And remember, Q is concentration of products divided by concentration of reactants, right? So the product of this reaction is cadmium 2 plus, the reactant is Fe2 plus, and we will ignore the iron solid and the cadmium solid, because remember, solids and liquids will not appear in the Q equation, right? So basically, we can calculate Q by dividing 0.10 by 0.60, all right? So that is Q, and when you work that out, that's equal to 0.013, right? So therefore, that Q value would go here, which is here, right? And then, oh, actually, I made a mistake. The 0.013 here results from doing all of this right here. So this Q value here goes here, and then you do your number crunching, and you get your EMF value being 0.013. So to answer the question, will the reaction occur? You have to say, well, whether or not the EMF value calculated is positive or negative. If it is positive, then the reaction will occur. If it is negative, then the reaction will not occur. So as you can see right here, the resulting EMF value is positive. So therefore, the reaction will occur, and therefore it's spontaneous. All right? So that's basically how that one is solved. All right? Any questions? Yes, sir.
E is greater than 0, so it's not that left for G.
No, delta G is negative would mean it's spontaneous, right? And because of the equation I showed you earlier, E would have to be positive if delta G is negative. All right? Okay, any other questions about this? Any other questions? Okay, these are just some examples of cells. As I said before, the way cells work is based on a very fundamental concept that a redox reaction is taking place, right? You have the cathode where reduction takes place and the anode where oxidation takes place. So this is just an example of a dry cell, an ordinary battery that you use in, you know, whatever devices that that you use. And here is the anode reaction in this case, and here's the cathode reaction, right? A bit more complicated than the ones that we saw earlier, but it's the same underlying process. And of course, you can add these two together to get the final equation, all right? Here is another one. This is a smaller type. And again, it's the same idea, anode reaction, cathode reaction, right? Add these two together, you get your net reaction. Excuse me. Here's another one. Now, this one, of course, you recognize as your car batteries. It's actually a series of cells. And let me just show you the equations for the anode and cathode reaction. So this is the anode reaction, and this would be the cathode reaction right here. And when you add these two together, you get your net reaction. All right. Now, this one is interesting. This one is called a solid-state lithium battery. The thing about this one is that there are no aqueous solutions involved, right? Basically, you have your lithium over here, which serves as the anode, and you have your titanium 4 sulfide, which serves as a cathode. And these are the half reactions right here, right? And basically, you have the lithium undergoing oxidation to form lithium plus, and you have the titanium 4 sulfide undergoing reduction to form this ion here. To be honest, I don't know what the name of it is. And that's basically how that works, all right? Okay. And then we have a fuel cell. And the last, I'll be honest with you, I've been checking up on this lately, but the last I read up on this one is that people are still working on it. This is basically seen as an alternative in terms of electric vehicles and so on. Basically, let me describe what's happening here. So you have your anode here, which consists of a carbon electrode, that's graphite, containing nickel, all right? And then here you have also graphite here. You have oxygen and hydrogen forced into these tubes right here. And these are the reactions that will take place at both the anode and the cathode. So this here is the anode reaction where oxidation takes place, where hydrogen reacts with hydroxide to form water, and of course electrons, which will go into the external circuit to drive this motor. And then this reaction here is the reduction half reaction to form the hydroxide ions, right? So basically, this is, as I said before, seen as an alternative to ordinary batteries. These are the two half reactions here. And the good thing about this concept is that the product of that reaction would be water. So that's why this is looked at as, you know, a more safe alternative to other types of fuels, right? The problem with this, if I remember correctly when I looked this up, is that you're going to need a continuous supply of the reactants, right? So we're talking about the hydroxide, the hydrogen, and the water in order for this to be continually producing electric current. And I think that once you get over that issue, then I guess it's all a matter of designing it for commercial purposes and so on. Okay, so those are just some examples of batteries. And let me see here. Oh, before we move on. Now, I don't know if you're familiar with rusting. Well, you should be familiar with rusting. Rusting occurs when you leave iron exposed to the atmosphere, moisture, and so on. And that converts the iron metal into rust. And the formula for rust is Fe2O3. And that is formed as a result of some electrochemical reactions taking place. Firstly, the iron undergoes oxidation to form Fe2+, and then the Fe2+ undergo further oxidation to form Fe3+, right? Now, the electrons that are produced, right, in this reaction would go towards reducing the oxygen, right, from the atmosphere, and any trace H+ ions present to form water, right? Now, the Fe3+ that is formed here will go on to form rust, right? Fe2O3, right? And therefore, that's how rust is formed. So therefore, you know, that's basically, those equations basically describe what happens when it comes to the formation of rust. Now, if you have a tank made up of iron and you want to preserve it, you can actually do that by attaching it to what is called a sacrificial metal, right? And in this case here, the metal would be magnesium, right? Now, the thing about the magnesium is that magnesium has, well, when it undergoes oxidation, forms Mg2+ plus 2 electrons, while the Fe will undergo oxidation to form Fe3+ plus 3 electrons, all right? Now, between these two, this one is more likely to occur, right? And that's because the EMF of the reverse reaction is low compared to this one, right? So basically, if you attach your magnesium to your iron storage tank, right, and leave it for a while, then the iron storage tank will not rust readily, right? The magnesium will undergo corrosion first, as described by this equation here, right? And therefore, you can maintain your iron storage tank for a relatively long time, all right? Okay, so that's as far as that is concerned. Let me scroll down and see what's next. Okay, you know what? I'm going to stop here for today because the next topic is dealing with the other type of electrochemical reaction, which is electrolysis. All right. So what we're going to do next class is we're going to, before we move on to this topic, we're going to, oh shoot, we didn't finish question, oh, we're going to finish question number 2 and then move on to question number 3. Yes, question number 3. Okay, also, let me get those persons who came in late. Let me make sure I record your attendance. Is Browning, you can get out of this here. Okay, is Browning here? I guess not. Cooley? Nope. Foraker? Nope. Gonzalez? Okay. Harvey? Okay. Joseph is here. Culp? Not here. Lozier? Not here. Messick? Not here. Ramirez? Not here. Retzlaff is here. Torres? Not here. And White. All right. Also, let me just say that I'm at the tail end of grading assignment number, what is it? Is it 4? Yeah. Yeah, I'm at the tail end of grading that, so you should get that back this evening. And I'm going to start on assignment number 5 ASAP. And I also posted the answer key for assignment number 4, but I have to make some changes because I realize that there's some errors in it. So I'm going to make the changes and then upload a corrected copy of that answer key. So that will be done later on this evening as well. All right.
You have some of the time for sure.
No. In my office waiting on me right on my desk. So. All right. So yeah, that's all I have to say by way of announcements. So I'll see you guys tomorrow.